What's up, class? Let's learn about some factoring. You may notice a lack of music. Well, it just occurred to me that my YouTube videos can be taken down because of using music that I don't own the copyright rights for. So we're going to avoid doing that going forward. Alright, so remember, take notes, rewatch confusing parts, and write down questions. Especially I'm making these videos in one shot because you can't really edit them. So I got to do it like in one 25-minute span. So there might be a mistake here and there. So if you think you see one, write it down. Write down like the minute number on the video. Bring it up in class, and we'll talk about it. All right, I am human. All right, so first notes about factoring. All right, you kind of look at this as a little flow chart. All right, starting at the top, you want to factor out the greatest common monomial. All right, so whenever you see a polynomial and you have to factor it, see if there's a common factor that goes into each of the terms. And then it's going to be three different things. If it's a binomial, meaning two terms, you're going to use one of these three formulas, and we'll learn what that means. But dot stands for difference of two squares, that stands for difference of two cubes, and sum of two cubes. So if you can identify the polynomial as a binomial, has two terms, and it falls into one of those categories, then you're literally just plugging into a formula. If it's a trinomial, then you'll do the AC method, alright? And you probably know what that is, or some form of it, but AC refers to, in a quadratic and standard form, A and C are A is the leading coefficient, and C is the constant term at the end. And if it's a four-term polynomial, we're going to factor by grouping. Alright, and we'll learn what that is if you don't know already. So let's just jump right into it. Alright, but this is just the kind of way you want to think about when you're factoring. Pull out the GCF first, identify number of terms, and then you do one of those three things. Alright, so here are those formulas that I talked about. So dots, difference of two squares, is in the top part. I just got to change the color so you can see it. Alright, so we learned about that yesterday, or last video, when we learned about special products. If we did a sum times a difference, it would come out to be a difference of two squares. Well, factoring is just the opposite direction. If you see a difference of two squares, you could factor it out as a sum times a difference. Alright, trinomials. Now this is just kind of relates to what we did in the last video, where we took a binomial squared and we got a perfect square trinomial, where the first term and the last term was the first and last term squared, and then the middle term was 2 times each of these terms. Alright, so if you ever recognize a quadratic in this form, it to be a perfect square trinomial, then you could just factor it as a binomial squared. But honestly, I don't think you're going to do that too often. You'll probably end up just doing the AC method. But like for example, on the right here, if you notice, alright, we got a perfect square in the first term, a perfect square in the second term. If you take the square root of x squared, you get x. The square root of 16 is 4. 2 times x times 4 gives you 8x. Alright, that's a perfect square trinomial, so you can factor it as a binomial squared. That's one way to go about it. But again, I would just use the AC method. Same thing if you see that this second term is negative, but everything else is the same. You can identify as a perfect square trinomial and factor. Alright, the sum or difference of two cubes. Alright, so if you see two terms, it's either going to be unfactorable, the difference of two squares, or the sum or difference of two cubes. Alright, if it's ever a sum of two squares, you cannot factor it with real numbers, and when we learn about imaginary numbers, we'll learn how to factor those. But for now, it's either going to be difference of two squares, two terms, or it's going to be two terms, and it's going to be the sum or difference of two cubes. Alright, so there's a formula that goes with it. So if you see a perfect cube plus a perfect cube, it's going to factor out to a binomial times a quadratic trinomial. And the signs follow the pattern SOAP. Alright, SOAP stands for same. So whatever the sign is first, if it's a plus, then the first sign is going to be the same. If it's a minus, then the first sign is going to be a minus. And then this stands for opposite. So the next sign is always going to be opposite the first sign. and then the last sign, AP, always positive. Alright? The last sign is always positive. And there's no coefficients. It's just if it's u cubed minus v cubed, it's going to be u minus v times u squared plus uv plus v squared. Alright, and that's something you want to memorize. And just a quick proof of it, if you took something like u, if you took something like u minus v, you know what, let me do a minus b, because it's easier to distinguish when you're writing. And then times a squared plus ab plus b squared. If we just multiplied all that out, watch what happens. So take this a and distribute it to all three. So it's a cubed, and then plus a squared b, and then plus ab squared, and then negative b times a squared would be negative a squared b. I want to put that in alphabetical order. And then negative b times ab would be negative ab squared, and then negative b times positive b squared would be negative b cubed. Alright, ignore that little dot right there. This one, ignore. Anyway, so this plus a squared b will cancel out with negative a squared b, and then plus ab squared will cancel out with negative ab squared, and you're left with a cubed minus b cubed. Alright, so we use that to kind of go in reverse and factor a difference of two cubes. And a similar proof could be made for the sum of two cubes. Alright, so let's apply some of these formulas now. Alright, first things first. Number 1. 6x cubed minus 4x. Well, the first thing you do, no matter what, is pull out a GCF. So the greatest common factor is exactly what it sounds like. If you were to factor this completely, so like 6 as 2 times 3, and then x cubed as xxx, and then minus 4x, which is 2 times 2 times x. Alright, so we have two terms, and they're factored completely. And they have factors in common, like an x and an x. Alright, they also, but that's not the greatest common factor. There's also a 2x, or just, a 2 and a 2 and an x and an x. So the biggest, the greatest factors that these two terms, 1 and 2, have in common are 2x. So to pull out a GCF means to pull out that 2x, right, and then just write what's left over. So it's kind of like you're doing the reverse of the distributive property. So you're left with 3xx, so 3x squared, and then minus 2. Alright, that's what it means to pull out a GCF. Alright, and then over here, we now have a two-term equation here, and you want to try to factor that. Now, if it says factor using only rational numbers, we would be done, because 3x squared is not a perfect square, and negative 2 is not a perfect square. But if it said factor completely, or use the linear factorization theorem, which is something we haven't learned yet, then you could actually factor this with the difference of two squares. But actually, as I think about it, I don't want to get into that yet. So until otherwise noticed, I just want to let you know that this technically could be factored a little more using irrational numbers, but for now, I just want you to factor everything down until it's a rational number. And then once we master that, we'll take it one step further. Alright, so we're done. Right here, boom. Alright, number 21, the next one. Look for a GCF. So, you don't have to use the method we did up here and factor everything completely. You could probably pull out the GCF like in your head. So, look at 20 and 30. So what's the greatest common factor between them? 10. And then a to the 6th and a. The greatest common factor would be a. And then b to the 11th and b to the 8th. The greatest common factor would be b to the 8th. Alright? Now, what's left over? So 10 times this first term, we put a 2, because 10 times 2 gives us 20. And then for the second term, we're still going to have two terms inside the parenthesis, is going to be a 3. Alright? Now look at the a's. So a times what gives us a to the 6th. So it's going to be a to the 5th. And then a times 1 gives us a, so we don't need to put any a placeholders there. We can really put a 1 there, but like it's eventually going to disappear because 1 times anything is itself. And then b to the 8th times b cubed gives us b to the 11th. And we still want to put a subtraction sign there because a negative times a positive will give us a negative. And then b to the 8th times 1 again will give us b to the 8th. So we're going to put another 1 there. But it's really not nice to write 3 times 1 times 1. So your final answer, it's not considered simplified if you do that, would be 2a to the 5th, b to the 3rd, minus 3. Boom. There it is. Checkmate. Alright, let's move along here. But, and before you move along, check to see if this isn't a difference of 2 squares. And it isn't. So you move along. Or it could be a difference of 2 cubes or sum of 2 cubes. Alright, we'll look at examples like that in a moment. But for these first 2 examples, I just want you to focus on pulling out the GCF. Alright, now, here are more complicated pulling out the GCF problems. Alright, so let's start off with E. Alright, we have 2 terms in E. 32x cubed 3x minus 4, and the second term is 40x squared times 3x minus 4x squared, or 3 minus 4x squared. So, they have factors, each of those 2 terms. Some of them are in common with the others. So, let's factor it out completely, or let's expand this out completely. So 32, that's going to be 2 to the 5th. So 2 times 2 times 2 times 2 times 2. Alright, and then times x cubed. That's going to be xxx. And then times 3 minus 4x. Alright, so that's expanded completely. And then plus 40x, which would be 2 times 2 times 2 times 5 times x, and then times 3 minus 4x times 3 minus 4x. Alright, so now these are expanded completely. And again, you don't have to do this, but starting off, it's a good method because it helps you find the common factors. So I see 5 factors of 2 in the first term, 3 factors of 2 in the second term. So that means they have 3 in common. So we can pull out these 3 2's. So that's 2 cubed on the outside. And then you have 2 x's here and 2 x's there. So we could pull out an x squared. And we also have a common factor of 3 minus 4x. Remember, that's just one quantity in parentheses. So you can treat that just like a variable. Because it's still an unknown quantity. It's just in the form 3 minus 4x. So we could pull out one of those. Alright, now, what's left over, if you were to distribute this factor back in, well, you would need to account for these 2 2's and that x. So that's why we're going to leave a 4x in here. And then this 5 and this 3 minus 4x. So it'd be plus 5 times 3 minus 4x. Alright, now we're just going to clean it up. So this 2 times 2 times 2, xx, that becomes an 8x squared. Alright, and then times 3 minus 4x. And now in the parentheses, so we have like kind of 2 sets of parentheses. Let me go back in red. We have this red set right here. And then inside of that, you got 4x plus 5 times 3 minus 4x. So you can actually distribute this 5 right here and get a 15 minus 20x. And then combine like terms. So you got that 4x over there. So this right here, that would simplify into this binomial, 15 minus 16x. And there you go. Now you should always clean that up after you pull out the GCF, like inside these parentheses right here, which I'll highlight in yellow. Inside like these parentheses, you want to always, distribute everything and combine like terms, because this part might be able to be factored more. Now it was linear, so it couldn't be, so that's your final answer right here, right above this yellow highlighted line. Alright, let me clear the page and let's try this one now. Now, there's kind of like two ways to look at this. So with the first way, let's use our exponent rules. So the first thing I'm going to do is get rid of that ugly yellow marker. That's the first thing I'm going to do. Let's go back to the white. Looks good on the black. Alright, so I'm going to rewrite this as x over 1 minus 2x to the 3 over 2 power. Because that's really what it means to have a negative exponent. We're just going to bring that 1 minus 2x to the 3 over 2 power in the denominator. And then plus 1 over 1 minus 2x to the 1/2 power. Alright, and remember, the denominator of 2 in the exponent here and here just means that it's the square root of 1 minus 2x, and then on the left being cubed, on the right being raised to the first power. So we can kind of rewrite this. Let's keep it all in rational exponents. So instead of doing the square root part, we could do 1 minus 2x and then to the 1/2 power. Then that's cubed. And then plus 1 minus 2x to the 1/2 power. Alright, so now in these denominators we have this common factor. We have this 1 minus 2x here to the 1/2 power and this 1 minus 2x here to the 1/2 power. Except on the left we have it being raised to the 3rd power. Alright? Now, let me just erase this stuff right here because that's kind of nonsense. Alright, now we can pull this out. We can pull out this whole factor of 1 over 1 minus 2x because it's a common factor of both of these. On the left side, we'd be left with x over 1 minus 2x squared. Alright, because we had it to the 3rd power in the previous step, and now we pulled out one factor, so now it's to the 2nd power. And then on the right side, we pulled out that entire term. So now we're left with that right there. And we have no negative exponents. And I ran out of room, but now if you really wanted to, you could, rewrite this all with one denominator by rewriting this as this number 1 here as 1 minus 2x squared over 1 minus 2x squared. And I'm going to run out of room in a second, but you could then rewrite that with one denominator on the right, and you pulled out the GCF, which is right there. Alright? Let me just show you another way to think about it. So let's do it again. I think this second way is worse. It's a little more complicated. Not complicated, but just less straightforward. So if you think about example up top, we had a 3 minus 4x factor raised to the 1st power and a 3 minus 4x factor raised to the 2nd power. So we pulled out a 3 minus 4x because that was the lower of the two exponents. Alright, we only pulled out one. In this example, we have 1 minus 2x to the negative 3 over 2 power, and that is the lower of the two exponents. So we can pull that out now. And then, what are we left with? Well, we're left with an x right there. And then we're left with a plus 1 minus 2x raised to the 1st power. Because this 1 right here is really like a 2 over 2. And if you were to like to distribute this back in, negative 3 over 2 plus 2 over 2 would give us the negative 1/2, and we multiply an exponent with one base times an exponent with the same base, we add the exponents. And then we'd be left with this term, 1 minus 2x to the 3 halves, negative 3 halves power, which you can write as 1 over 1 minus 2x to the positive 3 halves power times x plus, and then you get rid of this because that's just an exponent of 1, x plus 1 minus 2x. And then that becomes 1 over 1 minus 2x to the 3 halves power times 1 minus x. Alright, and if we took the first example and simplified that fraction by getting a common denominator, it would eventually look like this answer over here. Alright, so any method, either method is fine. Alright, now let's look at some factoring formulas. So each of these are two terms, and they're all difference of two squares. So if we start off with A, no matter what, always pull out the GCF first. So you can pull out a 3, and you're left with 1 minus 4x squared. And now, that's a difference of two squares. I can't write here anymore. I started too high off on the screen. Sorry about that. Alright, there we go. So, 1 is a perfect square. 4 is a perfect square. X squared is a perfect square. So we can factor this to 1 minus 2x times 1 plus 2x. That's because it's in this form, right? It's in the form a squared minus b squared, where 1 is a squared and 4x squared is b squared. So if a squared is 1, that means a is going to be 1. And if b squared is 4x squared, take the square root of both sides, that means b is 2x. So we just kind of plug that into this formula, a minus b times a plus b. Alright, so that's how I get that answer. In b, we got x minus 2 squared minus y squared. So again, if that's in the form a squared minus b squared. So if a squared is x minus 2 squared, that means a is going to be x minus 2. If b squared is y squared, then b is going to be y. So when we factor this, we're going to get x minus 2 plus y times x minus 2 minus y. And there's really not much else you could do there because they're unlike terms. Alright, and then in C, let's go with a different color here. That's also a difference of two squares. Alright, 16, x to the 4th, 81, all perfect squares. So if a squared is 16x to the 4th, that means a has to be 4x squared. And if b squared is 81, that means b is going to be 9. So you can take that and factor it to 4x squared minus 9 times 4x squared plus 9. But be careful. Not be careful, but always check before you move on from a factoring question that it can't be factored more. Because right here, we have another difference of two squares. 4x squared minus 9 is also a perfect square. So we can factor that even more. 2x minus 3 times 2x plus 3, but then times 4x squared plus 9, because that is not a perfect, that's not a difference of two squares. That's a sum of two squares, and you can't factor that yet. We'll learn how to do it with imaginary numbers later on. But for now, that's as far as you could go. Alright, so always check before moving on to factoring problem that things can't be factored more. Alright, let's try the other formulas. Now we have a sum of two cubes, so you just got to remember the formula, alright? So the formula would be, if you have a cubed plus b cubed, first it's always going to be a linear binomial times a quadratic trinomial, and there's no coefficients. and the signs go SOAP. So it's a sum, so the first one's same, and then the next one's opposite, and this is always positive. Alright, and if we look at what we're given, we know a cubed is x cubed, which means that a has to equal x, which means that a squared has to equal x squared, and we're given that, we're given that b cubed is 8, so b is going to be 2, and b squared is going to be 4. So now we're just going to plug right in. So it's going to plug in x for a, 2 for b, so we get x plus 2 times x squared minus 2x plus b squared, which is 4. Alright? Same thing here. Alright? A cubed is 27x cubed. So a is going to be 3x. And same. So this is a negative sign. Messed that up. Whatever. Let me erase that. That's a negative sign. So that sign's going to be negative. It's going to be 3x minus 1. And then plus a squared. So you take that and you square it. So you get 9x squared plus, same opposite. So this could be the opposite sign. ab. So you just multiply these two together. And you get 3x. And then plus b squared. 1 squared is 1. So that is how that factors. Alright, moving along. Let's do some AC method. So AC method is when you have a 3-term polynomial, so a trinomial, and a is not 1. So when I talk about a, b, and c, I'm talking about the coefficients in front of x squared, in front of x, and the last term. So in this case, a is 6, b is negative 13, and c is 7. And if a is not 1, then you want to use this AC method, which actually involves some factor by grouping as well. Alright, so for the AC method, you look for two numbers that multiply to AC. So a times c would be 42, because 6 times 7 is 42. So two numbers that multiply to AC and add to b. Alright? And if you have trouble seeing it right away, just start writing all the numbers that multiply to 42. But that would still add to negative 13. And since it has to add to a negative and multiply to a positive, you know both numbers have to be negative. So it's going to be like negative 1 and negative 42, or like negative 2 and negative 21. Then you eventually get to negative 6 and negative 7, and that's your AC. Or that's not your AC, but those are the two numbers that you need. Alright, so now we're going to take this, and the next step is you break up the middle term as the sum of these two numbers. So instead of writing negative 13x, you write it as negative 6x minus 7x, and then plus 7. Alright, once you do that, step 3 is factor by grouping. So look at the first two terms and pull out the greatest common factor. So you can pull out a 6x, and then you're left with x minus 1. And then in the next two terms, you could pull out a negative 7, and you're left with an x minus 1. And now you have two terms, each with a common factor, x minus 1. So you could pull that out. And then you're left with 6x minus 7. Alright? That's how you factor that. This one over here, we can use the same method. So we want to put it in standard form first. So we're going to write it as 10y to the 4th plus 11y squared plus 3. Now you might be asking yourself, this isn't a quadratic, and it isn't, but you can treat it just like a quadratic. Instead of in the previous example, we had like 6x minus 7 times x plus 1 or something like that. Our variables after we factored were x. Well, now it went from x squared and x to y to the 4th and y squared. So now in our answer, we're going to have, when we factor it, like a y squared term and a y squared term. So I just got to figure out what numbers go here, 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 and here. Alright, so AC method. So we're going to look for two numbers that multiply to 30 and add to 11. Alright, and after some thought, you can get that to be 5 and 6. So then we're going to take that middle term. So we have 10y to the fourth still. And we're going to break up that middle term as plus 5y squared plus 6y squared. And then plus 3. And we're still going to do the same exact thing. We're going to factor by grouping. So we're going to pull out a 5y squared here in these first two terms. And you're left with a 2y squared plus 1. And then here we can pull out a 3. And 3 times 3y, or 2y squared. 3 times 2y squared is going to give us 6y squared, and then plus 1. And then now you can pull out this whole term, 2y squared plus 1, and you're left with a 5y squared plus 3. And there's your answer. So there's a 2 here, a 1 there, a 5 there, and a 3 there. So you don't even really need to worry about these y squareds. If you just factor by grouping, they'll appear naturally. Alright, 2 more slides. Appreciate you watching this long. Didn't mean for this video to take forever. There's a lot of stuff for factoring. We'll be doing it all year, so you might find yourself watching this a couple times throughout the year, or at least certain parts. Alright, last thing, factor by grouping. Second to last thing. There's one more slide after this. So we're going to look for, it's kind of like the AC method, the second step, when you look for common factors in the first two terms and then pull them out. So in this example, so if you have 4 terms, you want to look for a common factor in the first two terms. So it would be a 2x squared, and you're left with x plus 2. Then look for common factors in the second two terms, the last two terms. So that would be a 10, and you're left with x plus 2. And now we factor by grouping. We pull out this x plus 2 because it's common in both terms, and we're left with a 2x squared plus 10. Alright, now something I forgot to do early in the question is check for GCF. I should have done that first. So because I didn't do that, I have to do it at the end. So I have a common factor of 2 that I could pull out between 2x squared and 10. So I could pull that out in front, and then I'm still at the x plus 2 from the beginning, but then I'm left with, instead of 2x squared, just x squared plus 5. Alright, and see if that could be factored more, and it can't, because although it's a perfect square here, it's a sum of a perfect square and a 5, which is not a special formula. Alright, another 4-term polynomial here. We could try to factor by grouping. So in these two terms, we could pull out an RS, and we're left with 2 plus 3t. And then, since both terms are negative here, we could pull out a negative 1, and they're both divisible by 4 and r, so you can pull out a 4r, and you'll be left with a 2 here, because negative 4r times 2 is negative 8r, and then we'd be left with a plus, because a negative times a positive gives us a negative, a plus 3t. Well, just 3 actually. And I actually made a mistake at the beginning. I don't know why I put a minus here. That should have been a plus the whole time over in the first term. Alright, so now that's our common factor. So we can pull that out. 2 plus 3t. And then we're left with rs minus 4r. And if you notice, again, I forgot to put out the GCF at the beginning. Each of these terms is divisible by r. So now I have a factor with a common factor of r in it, so I can pull that out. And then we still have 2 plus 3t, and then we still have s minus 4. So this would be our completely factored answer. Alright, so don't make the mistake I just made twice. Pull out the GCF at the beginning. Alright, last one. Something like this. Alright, how do we do that? Well, it doesn't look like a factoring question, but it is in fact a factoring question, because in order to simplify this fraction, we got to pull out a GCF in the numerator and the denominator and see if they cancel out. Alright, so one thing that might help seeing this question is if, let's say we just threw a number in there. Let's just say n was equal to 3. So then we add 2 to the third plus 2 to the second over 2 to the fourth minus 2 to the third. Alright, so in the numerator, I mean, we can add those together, but why not pull out a 2? We could pull out a 2 squared. We pull out 2 squared and we're left with a 2 here and a 1 there. Because 2 squared times 2 gives us 2 to the third, and 2 squared times 1 gives us 2 squared. And then over, we could pull out a 2 cubed here. And then we'd be left with 2 minus 1 on the bottom. And this 2 squared over 2 to the third, that would cancel out to just be 1 over 2. And then we'd have times 3 in the numerator and times 1 in the denominator. And we're left with 3 over 2. Alright, so whenever you get a question with a lot of variables, if you have the time, it might help to just play around with it and plug a number into the variable first. So let's do it for real now with the variables. So with 2 to the n plus 2 to the n minus 1, we can pull out a 2 to the n minus 1. Because we know that 2 to the n minus 1 times 2 would give us 2 to the n. Because you add, that's really an exponent of 1, you add the exponents when you multiply two numbers with exponents with the same base. And then plus 1, because that's just a placeholder for this 2 to the n minus 1. When we distributed it in, 1 times 2 to the n minus 1 would give us this term right here. And then over, so again, we're going to look for the lowest exponent. We're going to pull that one out. So we're going to pull out 2 to the n. Here, we're left with a 2, because 2 to the n times 2 gives us 2 to the n plus 1, and then minus 1. So when we distribute that back in, we get a negative 2 to the n. Alright, so now we're left with 2 to the n minus 1 times 3 over 2 to the n times 1. Now, this 2 to the n minus 1 over 2 to the n, this part right here, that's going to simplify to just 2. Because you have one less factor of 2 in the numerator, so they would all cancel out, leaving you with just a 2 in the denominator. Or you could do your exponent rules, and you could subtract. So it becomes 2 to the n minus 1 minus n, and then times 3. And then n minus n gives us, they cancel out. So you have 2 to the negative 1 times 3, and that would go in the denominator, which would be 3 over 2. Alright, so, wow, that was a long video. Apologize for making you sit through that, but again, we'll be doing this stuff a ton. I'll probably make you watch this in little pieces, maybe. Probably gonna eat my words, but we're gonna spend a couple days on factoring, so at least it's all in one place. So thanks for watching. I hope you found it helpful, and see you in class.